We're going to soon get to solving partial differential equations, but there's a couple other things we still need to do first. One of them is a bit of a review of ordinary differential equations, because we'll need them to solve partial differential equations. You're assumed to have already been through a course in differential equations to get to this point. So we're not going to review everything there. One thing we'll review is a technique called separation of variables. So let's go through that one, because we're still going to use this one in this course. Most other differential equation techniques we're not going to bother with. We already did series solutions and now separation of variables, but all the other stuff we'll assume you know or can remember or can at least recall if you have to. But anyway, let's get into this separation of variables. Let's take this pretty standard first order equation. And in fact, this thing's going to come up later a fair amount of the time. Separation of variables. First, we'll rewrite this y prime as dy dx. That's all it means. So here's the equation just rewritten. And we're going to start separating variables. You want to start getting all y stuff on one side and all x stuff on the other. And we treat this just like a ratio, dy over dx. So we'll first move the alpha y to the right. Now let's see what we can do. We divide both sides by y and then multiply both sides by dx. We have separated the variables. All the y stuff on the left, all the x stuff on the right. So now we can just integrate each side like that. And here's what those integrals are. We have to include the constant of integration here. So here's what it gets after we integrate. We do a little bit more algebra to solve for y itself, which says this, and e to the anything is always positive. So this is all positive, so we can get rid of the absolute value signs. So we have what y is some arbitrary constant times e to the minus alpha x. It has one arbitrary constant because it was a first order equation with no boundary conditions. If you had to, you could put this solution back into this equation and verify that it actually is a true statement. That's the basics of separation of variables, and it's also the basics. We're going to be using this solution to that equation later on over and over. So if you ever see this equation again, you don't have to resolve. But let's do another one where it's not a standard equation. Here's another first order equation, e to the x y prime plus y cubed equals 0. And we'll give this one a boundary condition. When x is 0, y is minus 1. So we start separating the variables. First, we express the y prime as dy dx. Start moving, let's see, we'll move the y stuff to the left, x stuff to the right. So here they are separated. We just did algebra there. So here we can integrate. Here's what happens after you integrate. Do a little bit of algebra. And here's the solution you get to this equation, but we didn't yet solve for this boundary condition. So we have this one arbitrary parameter in this general solution at this point. But we know if we put in 0 for x, the answer's got to be minus 1. So when we put in 0 for x, we get this. And when we had a y squared here, so we had to be careful and use plus or minus on the square root here. We don't know the sign yet. But this, with the arbitrary constant in it and the plus or minus, had to be minus 1. So So that means A equals 3, and we use the minus sign. So here is our solution that both solves the equation and satisfies the boundary condition. And again, if you put this answer in for y up here, verify that this is a true statement. There's some second order equations that we're not going to resolve. We're just going to state their solutions, because this equation, these equation types, these second order basic differential equations are going to come up again and again. And I'm just telling you, here's their solutions. So if you see these equations, you don't have to solve differential equations to get them. You just use these solutions all over again. One little remark on this middle one, this guy. There's two ways to express the solution. You can either use exponents, e to the alpha x, or hyperbolic trig. These are equivalent, although these arbitrary parameters would be different, but these are equivalent general solutions. And we're actually going to be using more often the hyperbolic trig version, this lower version. And our rule, this will come up later, but if the domain or where x is valid is infinite or semi-infinite, we'll use this form. But if the range of x is some finite, say from 0 to L or from minus L to L, we'll use this hyperbolic trig version. That's the one we'll be using more often. And of course, if alpha equals 0 here, you have this equation, and you just get this linear solution. So we're not going to resolve all of the differential equations that crop up. The only ones I hold students responsible for in my course is this separation of variables type, that technique. All other techniques, we're not going to recover. That would be in a differential equation course. So we're only going to cover the separation of variables techniques. The other ones, we're just going to use canned solutions. And here's a whole bunch of canned solutions. So if you see these differential equations on the left, you can just use the solutions, the general solutions on the right. Actually, this last one, we only have a particular solution. This last one is a Legendre equation. This one's a Bessel equation. We went through these in the previous charts. This, I believe, is a Cauchy-Euler differential equation. Is, well, two possible solutions if alpha is 0 or not. So anyway, we don't have to resolve these. These differential equations crop up. We're just going to use their solutions from a formula sheet. I'll go ahead and cover this one last chart in this little recording. Get used to Cauchy and Sinh, these hyperbolic trig functions. We're going to be using them quite a bit. Here's what Cauchy and Sinh mean, are their definitions. They're all real. There's nothing imaginary in here or complex. Here's what they look like. The sine is this odd function, this red function. The Cauchy is this even function, this green function. A couple of nice things. The derivative of each one is the other, without even a sign change, like normal trig. So the derivative of Cauchy is Sinh, and the derivative of Sinh is Cauchy. We can do that easily, and we'll have to. Another thing, when the argument of any of these guys is 0 or not 0, the function itself is not 0. The only place the Cauchy is never 0. The Sinh and the tang are 0 only exactly at 0. Another feature about the tang, which is this blue line here, it's got a slope of exactly 1 at the argument of 0. And everywhere else, its slope on the positive side is less than. It actually asymptotically approaches a slope of 0. That will come up a little later, that little subtlety. So I think, and we'll come back to this when we need to, but that's the introduction to Coach and Sims. Most students aren't all that up on it. So we'll stop there for this recording and get on with more material next time.